Thank you, Kristen. So this talk should be a good contrast to Eric's talk last night because I'm covering some of the same topics from a slightly different direction, so everybody can take away the viewpoint that you find personally compelling. So when I was writing this talk, one of the topic ideas I was kicking around was trying to illustrate what separated what you might call grown-up software engineering from, well, for want of a better term, kid stuff. And I collected some stories about some heroic feats of software engineering, such as how Stratus Systems. Anybody remember Stratus Systems? A few of you. Okay, so they made these amazing systems in the 1980s. They were fault-tolerant systems, which were super redundant, and they were designed to never go down under any condition. They could tolerate multiple hardware failures and all of that. But the really cool thing was that you could also update the device drivers in the operating system while applications were still running without losing connections. And this was one of those amazing, superhuman feats of software engineering that, would inspire us all. So I had some ideas for this talk, and I'm really glad I didn't write that talk because it would have looked really pathetic next to Anita's keynote yesterday, which gave us a glimpse into what real grown-up engineering looks like. So compared, to the challenges of landing a rover on Mars or building a self-sufficient system that has to live on Mars for years with no hope of resupply or repair, what we all do sounds pretty easy to me. And as software engineers, we also have a different sense of history than some of the other engineering disciplines. For example, in conventional architecture, we've known how to make buildings that could stand for 1,000 years for almost 1,000 years. And in software engineering, 5 years is a long time. A lot of the systems that we're working on, how many people here for the system that you're working on in your primary workday has been around for more than 10 years? So it looks like about 30%. So most of what we're working on has been built in the last 5 to 10 years. And as a result, a lot of the focus in what we do is aimed at building new systems to do something today and not necessarily to build them to stand for 1,000 years or even 10. Now, the system I work on is old by comparison to most software systems. This year, Java is 20 years old. And for the last 5, I've had the privilege of piloting the evolution of the Java language. And today I'm going to share a few thoughts on the challenges of evolving a mature platform, and a few lessons I've learned along the way, and a few thoughts on where we're going next, because we want to ensure that Java remains vibrant for the next 20 years as well. So the title of this talk refers to the slogan Eric mentioned last night, move fast and break things. So Facebook CEO Mark Zuckerberg advanced this as the motto for the Facebook engineering culture in the early days, basically telling the team that it was more important to make progress on improving the user experience than it was to worry about preserving what was already there. And this may have started at Facebook, but it's become, emblematic of the startup culture, and you're starting to see it, even filtering into open source projects as well. And it's not surprising that developers are drawn to a catchphrase like this. Breaking things can be fun, right? And it's often a lot easier to break things than to build them, and the parts that slow you down are often the boring and unglamorous parts, so who wouldn't want permission to ignore all of the things that slow you down? We do have to be mindful of the logical fallacy. Just because some progress entails breaking things doesn't mean that breakage indicates progress. Some people have that a little bit backwards. Now, this phrase really isn't about breaking things. It's about building things. Breaking things is rarely a good idea on its own. In fact, usually breaking things comes with legal and financial consequences. Obviously, the intent of saying move fast and break things is not to say go out and commit vandalism, right, or to celebrate destruction. It's to create the opportunity to build something better without getting slowed down by the need to preserve the status quo. And in other words, it's a way of giving people permission to value what could be over what is. And that's a pretty good thing. And giving permission to break things so that better things could be built in its place isn't really expressing a technological or a social viewpoint. It's expressing an economic one. So Zuckerberg was, knowingly or not, appealing to the work of the economist Joseph Schumpeter, who coined the phrase creative destruction to describe the inevitable fact of capitalism that progress comes at the expense of what came before. The growth of new industries like automobiles inevitably brings out the decline of old industries like horses. So it's notable that Facebook doesn't say this anymore. Last year at the F8 conference, Zuckerberg retired the old motto and offered this much less catchy one in its place. And this really was saying something. They're saying that yes, well, progress is still important, but not at the cost of destabilizing the user experience. So what changed for them? Well, when you're a startup with no users and a minimum viable product, the economics all point you towards making a lot of progress fast, regardless of the collateral damage or the accumulation of technical debt, because if you don't make some progress fast, you're going to run out of money, you're going to get scooped by the competition, and it's game over. When you're the market leader with a mature product, the economics point in a different direction, and you don't have as far up you can climb, and you have a lot farther that you can fall. So it's not surprising that startups are more concerned with progress than while more established businesses care more about stability. And for a good summary of this, we can look at the poet Bob Dylan, who said it pretty clearly: "When you ain't got nothing, you got nothing to lose." I'm not going to sing it for you. So move fast and break things is a sensible strategy when you're a plucky startup hoping to rise above the crowd to get some attention, but it's a less appropriate strategy when you have 1 billion users. And the point of all of this is the priority between progress and preservation is a business decision. Move fast and break things isn't a philosophy, and it's not a strategy, it's a tactic. It's a business tactic, and hopefully it's one supported by a sensible cost-benefit analysis of whether this is going to further your business goals or not. One of the things that separates the grown-ups from the kids in this industry is the understanding that programming is fundamentally an economic activity. Technology is exciting and it's fun, and we're all lucky that we get to do it for a living. I mean, I'm thrilled that I get to do what I do for a living. But technology is a means to an end. It isn't an end unto itself. If it were cheaper or faster to build Facebook out of rubber bands and duct tape than out of PHP, then that's what they would have done. And I know what some of you are thinking. You're thinking PHP is rubber bands and duct tape, and that's perfectly valid conversation, but that's a subject for a different talk. But if programming is economic activity, we should be able to measure the inputs and outputs. And so the inputs are pretty simple, right? You need programmers and you need pizza. And the outputs are a little harder to measure, but in any successful scenario, you're hoping to get some working code, and you're also bound to accrue some technical debt, which you could think of as the obligation to provide more developer time and more pizza in the future, assuming you're planning to stay in business. So moving fast and breaking things is a choice that I want to get more of both of these outputs, more working code, and also more technical debt for a given amount of pizza. And, in some cases where you've got nothing to lose and your investors are breathing down your neck, it can really be a smart choice. But again, this is a business decision based on business conditions, and those change over time. And it's important that we not confuse this for a philosophy. So by moving fast and breaking things, you're choosing to value time to market over stability and future maintenance costs, and sometimes that's a perfectly sensible decision. So to bring this point home, I've picked out a few quotes here from a great article I just found a few weeks ago by Jocelyn Goldfein called "The Right Way to Ship Software." So I'll skip to the secret. There's no right way to ship software. But it all depends on the business context. So Goldfein says, in a profession where we carry out decade-spanning holy wars over tab widths and capitalization, it's not surprising that people get attached to their development and release habits. But if shipping so much software has taught me one thing, it's to be agnostic. Different methodologies optimize for different goals, and all of them have downsides. If you maximize for schedule predictability, you'll lose out on engineering productivity. And this leads up to a plea that, to developers. Please stop asking, is this process good or bad? And start asking, is this process well suited to my situation? Now, Goldfein was, knowingly or not, appealing to the philosophy of Charles Saunders Peirce, sometimes referred to as the father of pragmatism, who in 1878 framed what is now called the pragmatic maxim. I know it's a little bit wordy, so I'll summarize it for you. Pragmatism means judging a thing based on its practical effects on the world around us rather than on their innate properties as we perceive them. So, and we're all like to think of ourselves as pragmatists, as engineers, so it's useful to go back to what pragmatism really means. And you could imagine that Peirce is in turn appealing to the works of a much older philosopher from a galaxy far, far away, who might have said, although he didn't, "There's no good, there's only good for." And if Master Yoda had said this, what he would have meant is that as engineers, who are supposed to be pragmatic, we need to be willing to look past our own aesthetic and principled beliefs about what is good and what is bad, and instead judge things on the basis of whether they work in the real world. And we should judge the good of something based not on its intrinsic properties, but on what it is good for. So, in that light, what do we think of this move fast and break things strategy? Well, as probably no one will be surprised, if we say either good or bad, we're wrong, right? The answer is, it depends. Is it right for the situation? So this brings me to the main topic of my talk today, which is about engineering closer to the bottom of the stack, and how the engineering decisions you make in that context are different from what a lot of us are used to. And one reason why this might be more relevant to you than you might initially think is, as our careers as engineers progress, we have a tendency to move down the stack. Not because we make a choice to move down the stack, but because the stack is growing above us. There's more layers up there now than there were 20 years ago. So if you're comfortable at a certain layer of the stack, which might be the middle when your career starts, it's going to be closer to the bottom as you get later into your career. So you need to think about this. So I Googled around for some Java software stack diagrams. So I found a lot. Here's one I found internally. This is the Oracle middleware stack. Most of these are Java-based software services, for building applications, and you can see, there's Java there at the way very bottom. Actually, in the official version of this stack, it doesn't even show Java because they can't even see that far down. But here's another one. This is the Spring stack, and again, what you see is Java's down there at the bottom, right? And of course, it's not really the bottom, right? Below that you have containers and virtualization, operating systems and hardware, but it's the bottommost part that's visible to the developers in the programming model. And when you're the platform that everything depends on, moving fast and breaking things isn't such a great approach. Because down here, the term for breaking things is bug, right? And with millions of users, there's no such thing as, we can change that and no one will notice, right? Everybody notices everything. It's really scary. So when you're down here, you have to place a very high priority on stability and compatibility. And there was a time in Java's history when it wasn't the bottom of the stack, or even part of the stack. And in those days, we did move fast and break things. The amount of churn in the language and the VM design, leading up to the first release was really pretty incredible. But success comes with a price. And once you have users counting on you, your choices are a little bit more constrained. So when we talk about not breaking things, of course, we don't want to break our users' code, right? But this aversion to breaking things doesn't end just with the code. The people part matters a lot. We don't want to break our users' expectations, or their confidence in the platform, or their mental models of how things work, or the value of the investment they've made in their technical skills. And each of these forms of people compatibility adds additional constraints to how we might evolve the platform. So, in my role as architect for the Java language and also for the core libraries, my job is to shape the developer's view of what Java is, the user-visible programming model. And, of course, there's no shortage of, let's call them helpful suggestions that I get from developers in the community. Eric had one on stage last night. But there's a big disconnect from my perspective between what people think I do and what I actually do, so I made some charts to illustrate the difference. So here's one possible view of what an industry-focused language designer does from the perspective of our academic colleagues. And in this view, my job would mostly be about the technical aspects of language design, creating more expressive type systems, adding features that let us express more kinds of programs safely, or to make the intent of the program more clear. And, okay, these things are part of my job also, but this view completely omits the human side of it. When we're doing a particular group of features, we will have, of course, a time budget and a resource budget to get it done, but we're also mindful of what we like to call our complexity budget. A complex feature might allow you to do some really cool new things that express some interesting and valuable new programs, but it can also do a lot of damage, both directly and indirectly. So directly, a complex feature can cause damage because it's easier to misuse. And indirectly, it can cause damage by distracting the developer from the task that they're really trying to accomplish. So keeping it simple means that things can actually be used and used correctly by real developers. And even simple and otherwise sensible ideas might be discarded on the basis of cultural constraints because they're too disruptive or they're just too different from the existing mental models of our developers. So for example, and to take an example from Java 8, in Scala, if you have conflicts between members inherited from multiple traits, the conflicts get resolved by linearizing the supertypes. You give priority to the ones that appeared first in the extends clause. Totally sensible way to do things. Except we couldn't do that in Java because Java developers have 20 years of experience that tells them that the order in which the supertypes appear doesn't matter. And to yank that out from under them and say, oh, just kidding, for the last 20 years it's been this way, but now the gong rings and all of a sudden your program semantics are frozen the way they are, people aren't going to be happy about that. Would have been very disruptive. So these considerations are something that someone coming from an academic programming language background might never think about. But when you're evolving a platform used by millions of developers, they become very important. So this next chart is a little bit less charitable and therefore more fun. And this is what I sometimes think people in the community imagine I do based on what they say. So if you proceed around clockwise from the top, you've got your secret backroom meetings, and then every once in a while you poke your head out of the secret back room and you make some obnoxious comments on a mailing list. Maybe you come to a conference and make some self-promoting comments. And and from a technical perspective, it's mostly about stealing features from other languages. And of course, the most important topic is syntax. Now, it's fun to complain about how people don't understand what you do, and certainly it's somewhat therapeutic, but it's also important to remember that these are the people we're doing it for. So in some sense, what success looks like is not correcting their wrong ideas about how it works, but just making it work better anyway. Now, James Gosling described Java as a blue-collar language, and what he meant was it's a tool for working programmers to get their jobs done. It's not an ivory tower creation, right? And there may be a lot of rocket science in designing it or implementing it, and certainly in specifying it, but you shouldn't have to be a rocket scientist to use it. And we heard from a real rocket scientist yesterday. And of course, we want to have a broad spectrum of users, right? And we can't alienate any of these segments of our, of our user base. We need to have a wide range of users, but otherwise we risk sight of losing where's the mainstream going. So while Java primarily today may have its home in server-side business logic, we can't afford to alienate the high-frequency trading crowd because they may be niche today, but some of those concerns may be mainstream tomorrow. Okay, so this version of the chart is a little bit closer to reality from my perspective, and there are some structural similarities with the previous chart. There's definitely a slice for meetings and interacting with the community, but what's really different is the technical focus. If you look at some languages, it seems like the goal is to add every feature possible. And certainly if you listen to the users, what you get are requests, or sometimes demands, for more features. But in reality, adding language features should generally be your last resort. And because every feature adds some bad weight to the language. Every feature may interact with not only every feature that's already there, but it may interact with features that don't exist now but that you're considering for the future. And so we have to choose our features very carefully because we're going to be living with them for a very long time. And a perfect example of this, which is on the chart here, is serialization, which has managed to interact with every single feature we've added since. And for example, in the process of adding lambda expressions in Java 8, the interaction with serialization took literally hundreds of hours of analysis and discussion. And I tell you, I want every one of those hours of my life back. The remaining slices mostly have to do with the consequences of feature interaction. A common misperception about language features is that the hard part is either the idea or the implementation. And of course, these are important. But for the most part, we consider these things to be the first 0% of the work. Right? That they're needed to get started, but that's not where the hard work is. The hard work comes from fitting them in with the existing features you have and analyzing and testing them for interactions with other features, and not just with the features you have, but with the features that you might have in the future. And the most important aspect of this is the compatibility analysis, analyzing the compatibility consequences of everything. And of course, there's serialization. Now, the really fun part, and the part I get to do just a little bit of the time, is this slice here at the bottom. That's what would James do, right? That's where you get to go into your cave and meditate on what is the true spirit of Java. I get to do that for about 3 hours a year. But it's good. Okay, so let's come back to this theme of don't break anything. The biggest slice on the previous slide was compatibility. And compatibility comes in a lot of forms, and we worry about all of them. The most important of these is binary compatibility, and this is about whether call sites that are embedded in your class files will continue to link when you run them, against other newly compiled class files. You remember, all method invocations and field access in Java are dynamically linked at runtime. They're linked by name. There's the name of the method, the name of the signature is embedded in the class file, and it gets connected at runtime with the with the method that you're trying to call. And dynamic linkage is like one of Java's secret weapons, right? This is what enables you to just drop a new jar in your class path and not worry about it. But it's actually a pretty strong constraint, and class files that are compiled in 1995 still run today, and we expect that they should still run in 20 years, even though linkage is happening every time you run your program. Source compatibility, another form of compatibility we worry about a lot. That's whether clients or subclasses will continue to compile after you make a change to a class. And so I've changed superclass, I go to recompile my subclass, does it still compile, right? That's source compatibility. There's behavioral compatibility. Do things continue to work the same way after a change? There's, of course, serialization compatibility, bring up my favorite subject. Instances that have been serialized on an older JVM or maybe a newer JVM, will they deserialize properly? And then there's a whole host of more subtle compatibility issues, such as changes in the in-memory footprint or the performance characteristics. And, there's this cross-cutting concern that cuts across all of these compatibility modes, which is separate compilation. So because of dynamic linkage, you're always having to deal with the fact that part of your system may have been recompiled and part of it hasn't been. And normally, if you follow some reasonable rules for evolving your code, this doesn't, turn out to be a problem. But these things can show up if you change your compilation code generation strategy, or when the generated code for a class depends on information from other classes. This shows up with bridge methods, that are a consequence of generics. And, it's happened more than once that an otherwise worthy idea has gotten dropped because we have an ongoing compatibility concern, whether it be a binary compatibility or source compatibility. And that's not to say that we would never, ever violate any of these forms of compatibility. After all, you can't fix a bug without violating behavioral compatibility. On the other hand, there are times we don't fix bugs for that reason. And so, it has to be a very careful decision. So after sufficiently quantifying the amount of code that might break, we can consider whether this is the right thing to do, but it's not something that we do very lightly. Now, a lot of people think we're crazy to be this concerned about compatibility, but my claim is there really isn't any other responsible choice. When you have billions of lines of code out there, nearly any incompatible change is going to break someone's mission-critical code. And some people say, so what, right? But I think it takes a certain kind of arrogance to say, yeah, you should break his code. It'll be for his own good, right? But still, people actually say this to us with some frequency. And I'm sure they think they're being helpful rather than arrogant, but the mistake that they're making is they're only focusing on part of the picture. And what I see is that developers tend to overestimate the importance of code and underestimate the importance of stable programs. Now, this shouldn't be surprising to anyone, right? What do developers stare at all day? Code, right? So for them, it's their whole world. But it's really only part of the picture. It's just the part of the picture they see all day. So it's a little bit like one of those optical illusions where, depending on what part of the picture you look at, you see a different answer. Does everybody see it? Good, evil, good, evil. Okay, good. So, when users look at a language feature, they're imagining all the good things they could do with it, which is great. That's what they're supposed to do. They're imagining, what code could I write with that I can't write with the language that stands today? And when we look at a language feature, we do the same thing, but also we have to look at the bigger picture of not only how it might be used, but how might it be misused? How might it interact with other language features? How it might change the style in which developers program? How it might affect the migration of existing code to use these new features, and whether it'll cause subtle changes, and whether those changes are overall good or bad for the ecosystem. So when we look at the changes and how they might affect your code, we're not thinking about how it will affect your code. We have to be thinking about how does it affect everybody's code. Now, at this point, you're probably getting a little bit depressed, right? You're probably thinking, well, it's impossible to change anything. How can you make any progress if you can't change anything? And so you might conclude the sensible strategy is just do nothing, right? And that is a guaranteed path to compatibility, but it's also a guaranteed path to irrelevance. So evolving things compatibly is not impossible, it's just harder. And it's like working in pretty much any other difficult environment. You have to approach the situation with the proper precautions and training and safety equipment. So you got to suit up. This is an actual picture from our offices. No, just kidding. Okay, so how do we do it? Well, if it's not acceptable to change the meaning of existing programs, a language designer's next best trick is to expand the range of valid programs that you can express, so to assign meaning to programs that previously were invalid. So ideally, what you want to do is add features so that they abstract over other existing features. So instead of adding a completely new feature, take an existing feature and extend it to a broader range of situations. The reason we prefer this is that this builds on the user's existing mental models of how things work, and is also less likely to create interactions with other features. Now, the really hard part in this is coming up with a sensible semantics for the abstracted feature such that when you restrict it to the conditions where it used to be valid, they match up with the existing semantics, right? That's the hard part. So I'll give a quick example of this. This is like, I think, the only code in the talk, so apologies if you're not Java programmers. So if we were going to start, so a good example of this is when we added default methods in Java 8. So Java 8 adds default methods. You can add behavior to methods and interfaces. It's a form of multiple inheritance of behavior. Not multiple inheritance of state, but multiple inheritance of behavior. And if we were starting from scratch with multiple inheritance of behavior, the rules for resolving conflicts when you're inheriting behavior from two different supertypes probably would have been very different from what we came up with. So to summarize briefly, in Java starting from Java 1.0, interfaces could contribute only type information and members. So you have interface I with member M, and then class C has a member M, and then you have this class D that expends both C and I, and what happens there is when D inherits M from both C and I, the compiler just merges the members, because it says, okay, I have a contract declaration in this supertype, I have an implementation in that supertype, I'm going to declare them to be the same thing, and everything's good. So in Java 8, we added the ability to add behavior to the interface by marking it as having a default implementation, which can be inherited in classes that don't declare the method. But now, if you look at D, you have it inheriting behavior potentially from two different supertypes. So that's a conflict that has to be resolved. And we want adding a default implementation to be a binary and source compatible change. So we don't want D to all of a sudden be broken and have the compiler say, well, you have a conflict now, you have to resolve it. And so, what we did here is we looked at how does the existing semantics, behave, and let's find a way of defining the semantics of multiple inheritance to be, to be consistent with that. So what we did was we used a standard evolutionary trick, which was to adjust the rules to give the priority to the old way. So when resolving a conflict, we have three rules. Rule 1 says we prefer the implementation from a superclass to that of a super interface. So if there is an implementation in the superclass wins, we don't even look at the interfaces, and this gives us absolute compatibility with this existing code, because this rule 1 is how things worked, before we added behavior to interfaces. And then, the second rule is if two interfaces have an implementation and one's a subclass of the other, we prefer the subclass. That's pretty obvious. And then the third rule is, well, there's no rule 3. And then the programmer has to resolve the conflict by overriding the method and picking which implementation they want, right? So this is what I meant by, adjusting a feature to fit in with other features, right? The rules that we arrived at, that implementations and interfaces are just defaults and they're subordinate to the implementations and classes, probably wouldn't be exactly what we came up with if we were inventing an object-oriented language with multiple inheritance of behavior from scratch. That's okay. This is also a perfectly reasonable and sensible model, and there's more than one reasonable way to design a programming language. And we've used this trick before. This is the same trick we used when we added autoboxing in Java 5. So we added these new implicit type conversions where you could convert from an int to an integer. And this is great, except that all of a sudden the set of applicable methods now is larger than it used to be, and that could perturb overload selection decisions. And we didn't want code that used to compile to not compile because now the overloads are ambiguous. So in order to keep this from being incompatible, we took the overload resolution rules. We said, take the old rules, that's step 1 in the new algorithm. And then if step 1 doesn't come up with anything, then we move on to step 2, which is consider boxing conversions. It's a trade-off of complexity for compatibility, and if you don't make that trade-off too many times, you don't get mired in complexity. If you do that over and over and over again, eventually the rule set gets so complicated that you don't want to deal with it. But if you do it judiciously, it's a pretty good trick. So I call this strategy embrace and extend because first you have to embrace the existing semantics before you can find a sensible generalization that both stands on its own and matches the existing semantics. So this is like one of the tricks that we have in our toolbox. All right, so I'll talk a little bit more philosophically now about the things that we learned. The previous example, default methods, this worked out pretty well, and we were pretty happy with how that came out. But the idea did not spring fully formed on day 1. It took probably 2 or 3 years from the time we first cooked up the crazy idea of what if we could attach behavior to interface methods, and the time we arrived at a sensible model that Java developers don't look at and say, what is this alien contraption you've nailed onto the side of my language? Well, people say that anyway, but some people don't like to learn new things. And so, the solution, of course, of how you get there is iterations. We went through a lot of iterations of the language design, for this. And each one seemed like an improvement over the previous one, but it probably wasn't until we got to about the 6th iteration that we got it down to something that was simple and clean enough that we could fit on one slide, like the slide I just showed you. The danger is, because each iteration was simpler than the previous one, at almost any point, we could have easily made the mistake of saying, oh, we must be there, because it's definitely simpler than what we had yesterday, and it's way simpler than what we had last year. And we could have easily convinced ourselves we were done. And the reality is it takes a long time, and sometimes a lot of iterations to find the right idea. And more than once, I had to tell my management, actually, the man sitting there, hi, George, we weren't there. We're not there yet, and it's going to take longer. And thankfully, the answer was always take the time to get it right, because when contemplating something that you're going to have to support for 20 years, and it's going to constrain your evolution over the next 20 years, you want to be able to take the time to get it right, or be willing to not do it at all. So I recently came across this quote, which I think really echoed our experience here. This quote is from Steve Jobs, where he says, when you start looking at a problem and it seems really simple and you have all these simple solutions, you don't really understand the complexity of it. And then you start to understand the complexity, and your solutions are really complex. And that's when you're at the middle of the process, and that's where most people stop. And the solutions there tend maybe to work for a while, but the great person will keep on going and find the key underlying principle of the problem and come up with a beautiful, elegant solution that works. And the really hard part is when you found something that feels like it works, realizing that you might still be in the middle, and you probably are still in the middle, and having the faith to keep going, that there might be a better answer in there, even if you don't know what it is, because it's really tempting to just declare victory and stop there. Because after all, you've been thinking about this for 2 years. You know the problem is complex, and yes, your solution is complex, but of course it's complex. It's a complex problem. Right? And externally, you could be dealing with forces pushing you to ship what you've got, and you need to be able to take the time to find the simple solution that's lurking in the complex solution. And it's amazing how often this happens if you give yourself the time to do it. An even more extreme example of this is generics themselves. So last year at Java 1, James Gosling told this story about why generics weren't included in Java from the outset. And it's not because we didn't understand parametric polymorphism in 1995, and it's not because we thought it was a great idea to have a static type system that wasn't strong enough to let you put typed elements into a container and not retain their types when they come out. It's because we didn't know how to do it right. And if we had kept going anyway, we would have ended up with something like C++ templates or patterns from Beta. And I think we're all pretty glad we didn't get those solutions in Java 1.0. And it may have taken 10 years to get there, but the generics we got were much closer to the spirit of the language. And the generics we would have gotten in 95 would not have been. So if you don't know the right thing to do, at least don't do the wrong thing. And sometimes that means doing nothing. And you have to be okay with that. Another way to say this is reality hardens like concrete. Before you do anything, there's lots of paths forward. Once you do something, there are many fewer paths forward, and maybe only one. And this is true for the little things as well as the big. So always be thinking about what doors are you closing in addition to the doors you're opening. A related aspect to this lesson is you need to be skeptical of the inclination to punt on the hard cases. When you're tempted to punt on some case because it's too hard, that's generally a sign you're not at the middle yet. Sorry. Well, the question is, what does punt mean? Give up. Say, oh, forget about that. I'm just gonna ignore that. It's a term from American football. So the reason this sense of finishing the job is so important in language design is that what might seem like a clever compromise of we're going to handle cases A, B, and C and forget about case D, this may seem like a good compromise today, and tomorrow it is just another incomprehensible irregularity that makes programmers crazy. And it's often tempting to give into that because you can at least say, well, it's better than it was before. Before A, B, and C didn't work at all. Now A, B, and C work, and we still haven't solved D, but that's got to be better, right? But irregularity really bothers developers, and for good reason, because irregularity breeds complexity, and complexity distracts you from the programming task at hand. So the kind of naive suggestions that we sometimes get of, well, just make another language restriction that you can't do this when that happens, it may seem like a practical shortcut, but it's always going to be tomorrow's what in God's name were they thinking topics. So this last bit of advice might sound almost like the opposite of the previous one, which advises against accepting irregularities because building a regular solution is too hard. The opposite of that, which is also important, is to be skeptical of the motivation to do anything for reasons of consistency. Consistency is a good guide, and of course, but we often, allow the desire for superficial consistency to replace a deeper analysis of the problem. And I came to this by observing many of the most poorly thought out suggestions that we get always start with, for consistency we should do ... And invariably, these are terrible ideas, and they're just people are justifying it by consistency. Well, the reality is when you have a complex system, you can find a consistency excuse for anything. Right, and so when consistency feels like the best explanation, you got to dig deeper. And of course, that doesn't mean consistency is a bad goal. It's a great goal, right? Just don't use it to justify anything. And we have this great quote from the American philosopher Ralph Waldo Emerson: "A foolish consistency is the hobgoblin of little minds." This is often misquoted, though. People leave out the word foolish. So just be aware that some consistencies are foolish, and guard against that. Okay, so I want to talk just a little bit about where we're going in the future. I talked a little bit about some of the lessons we learned during the Java 8 evolution. And Java 8 was a great upgrade. It was probably the biggest upgrade to the Java programming model ever. It involved coordinated updates to the language, the library, and the JVM. And we're seeing renewed excitement over Java in the community these days, which is great. So we're done, right? Time to rest on our laurels? Of course not. Okay, so how do we pick the things that we decide to work on? Because we can only work on a few things. We don't have infinite bandwidth. We have a limited budget, a limited complexity budget, so we have to pick our targets carefully. And our approach for picking targets, I think, is a pragmatic one. Look at the pain points that developers and deployers are suffering from, pick the biggest one, and beat on that. So in Java 8, these pain points were mostly language-driven, specifically improving the ability to abstract over behavior using Lambda expressions. That was great. In Java 9, our focus is on the pain of programming in the large, reducing the pain of assembling large applications out of components and using those techniques to modularize the platform itself and get us out of class path hell, or jar hell. But pain points can also come environmentally, so sometimes they bubble up from the hardware. And since we want Java and the JVM to continue to run well on the moving target of modern hardware, every once in a while we have to look at Java's relationship with the hardware. So let's talk about hardware for a second and how it's changed in the last 25 years. And the summary is a lot, right? Most of us don't pay attention to this on a day-to-day basis, which is great. But hardware has really changed dramatically in the last 20, 25 years. in the very old days, we had systems that were single core, single socket, so the green thing represents your core and the blue thing represents main memory. They had no cache, no instruction level parallelism, no pipelining. So in those days, an arithmetic operation cost about the same as a memory fetch, on the order of 1, 2, 3, 4 cycles. So the performance model was really simple. Count instructions. You could just do it statically. You could look at the assembly dump of a program and model its performance in your head. Over time, our systems got more complicated. So we added cache, and then we added multiple layers of cache, and then we added multiple sockets, and we added multiple cores, and the core counts grew. And as these systems got more sophisticated, the cost of memory access got less predictable. And it ranged from a couple of cycles to get something that's in your L1 cache, to a few hundred cycles if you cache miss all the way down to main memory. Usually 300 cycles is a reasonable estimate for a full cache miss. And at the same time, the cores got more complex with deep pipelines and superscalar execution, and we can execute 4 arithmetic operations on a single cycle. So if a cache miss cost you 300 cycles and you can issue 4 arithmetic operations in one cycle, a cache miss is now costing you potentially 1,000 instructions. So 25 years ago, 1 to 1. Today, 1,000 to 1. Now, it stands to reason that given a 3 order of magnitude shift in the cost model, whatever engineering trade-offs we made in 1995 about how Java lays out data in memory can't possibly be optimal for today's systems unless we got really lucky and we've been suffering with some really bad decisions for the last 20 years. So it further stands to reason that periodically we need to update these things. So let's look at the JVM type systems. You've got your 8 primitive types, you've got objects, you've got arrays. And this is super flexible. You can model anything you want with this. But the flexibility isn't in exactly the right places. So primitives are more rigid than we'd like. If you want to represent a 65-bit integer, you're out of luck, right? You have to do that with objects. And objects are really flexible, but sometimes more flexible than we need. And the big issue is every object has identity, which exists to serve mutability and polymorphism, but not all objects need this, even though all objects pay for it. And you might think that the VM would just be able to figure it out and optimize around this, and VMs have gotten really good at slicing through the cost of code abstraction, but they never really got very good at slicing through the cost of data abstraction. And the reason for that is that the VM can never really figure out whether an object is going to need its identity or not, because any code can use any object as a lock at any time, and so the VM has to be pessimistic in the way it lays out data. So to illustrate this, imagine you've got a simple tuple-like class like an XY point. And let's say, this is an immutable class and it's final, so it's not polymorphic, so it doesn't really need an object identity, but it gets one anyway. So now let's say you've got an array of those things. So the array has an object header, and each element of the array is a reference to a point object, which has its own header. And, from a memory efficiency perspective, we're not doing very well, right? We've got 2 words of data, and for each one of those, we've got 2 words of object header and a pointer. So that's like 60% overhead, right? Because these objects are allocated on the heap, that's going to be work for the allocator on the garbage collector. And after garbage collection, they may even get shuffled in memory, right? But the real cost comes from the indirection cost of these pointers. So if you're walking your way through an array of ints, you get great locality, right? So you pull the first one in, and it pulls the next 7 or 15 into the cache line, and by the time you're on the 3rd or 4th, the hardware prefetcher is kicked in, and it's already pulled the next slug in, and everything's great. On the other hand, if you've got an array of objects like this, you may cache miss on every one of those dereferences. And cache misses, like I said before, can be really expensive. Now, maybe this is fine. Maybe your data set is small. Maybe your performance requirements are moderate, and it's not an issue, which is actually the case for 90-95% of Java deployments. But if you're doing something like high frequency trading or big data analytics, these costs really add up. And you didn't really ask for this layout, right? What you'd really rather have is this layout. You have an array of XY points. You'd like them to be laid out XY, XY, XY. Now, when confronted with a situation like this, developers sometimes take things into their own hands. Sometimes they have to, sometimes they just can't help themselves. But developers will do ugly tricks like this, where they'll shred an array of XY points into 2 arrays, one of X's and one of Y's, hoping to regain the locality that they lost. And this code is harder to write, and it's harder to read, it's harder to maintain. And the sad part is developers often do stuff like this for performance reasons with no actual evidence that their code isn't already fast enough, or maybe in fact without having performance measurements or goals at all. But regardless of whether developers do this out of genuine need or out of some destructive obsessive compulsive disorder, we have to blame ourselves for this to some degree, right? We've put developers in a situation where they feel like they have to choose between the good stuff, good abstraction and encapsulation, and good performance. And if you put people in that choice, sometimes people will choose wrong. So this brings us to the feature that we're working on. It's a VM feature, and it's designed, because of the change in hardware characteristics, which is value types. If we recast this point class as a value class, what we're saying is we don't care about identity, we don't care about all the baggage that brings with it, and by giving up on this flexibility, we gain the ability to treat it as a value. So values are implicitly immutable and final, and they derive their equality from state rather than identity, which means they can be passed by value. You can pass them in registers or on the stack instead of on the heap. And this means that if you have an array of them, they automatically flatten into an array, and if they're embedded in classes, they automatically get flattened into their enclosing classes. And so when you traverse them, you don't have those indirections that you had in the previous example. So the cool thing about values is they can have most of the things classes have. They can have methods and constructors and fields, and their methods can be private, and they can be generic and all of that. And because they're not polymorphic, there's no dispatch cost when you invoke their methods. And so you can essentially use them as cost-free wrappers that give you abstraction with no runtime cost. So this is great. And so our mantra for value types is codes like a class, behaves like an int. And the applications for this are obvious, right? Alternate numerics, tuples, algebraic data types like optional or choice, STL-style cursors. And there's no expressiveness benefit here. You can't write any new programs that you couldn't write today with objects, but what it means is it lets you do that without worrying about the cost. And we definitely worry about cost as programmers, even when we shouldn't worry about cost, because we're wired to worry about performance. It's just how we're built. So by making the right thing also be the fast thing, we remove a whole set of sources of friction from the development process. And because value types have access to encapsulation just like regular classes, we can use them, like I said, as secure cost-free wrappers around sensitive data, and get this free lunch of safety, maintainability, and performance. So that's really cool. I've been working on this for probably a year and a half, and we're getting close to having a design that works. It takes a long time. We've got a prototype in OpenJDK if anybody's interested. Okay, how does this interact with generics? Remember I said you add a new feature, it interacts with everything else you've already got. So, when you look at generics with box primitives, we have the same layout problem we had with the array of points before. We have an inefficient data layout, too much indirection, bad locality, too much allocation. So if we have an array list of box integers, you have an object for the array list, and an object for the array, and then an object for each element. And once you add values to the language, you immediately see that this sort of uneasy irregularity that we embraced in Java 5, which is you can't generify over primitives, you can only generify over references, that starts to fall apart. It worked for a while. Remember, like Steve Jobs says, those things work for a while and then they fall apart. Well, we're hitting that fall apart point. When there are only 8 primitive types, you can look the other way. But once we add user-defined primitives, it really has to work with generics. So, we're going to have to bite the bullet here, and this involves VM work as well as language and library work to support generics over primitives and values. So you could say, I want an array list of ints, and I actually have it backed by a array of ints, under the hood. So these two features that kind of work together, value types and generics over primitives, are part of actually a larger effort to reboot the JVM's relationship with memory and the underlying hardware to try to balance the need for abstraction and encapsulation with the performance reality of modern hardware. But I think it's a pretty cool example of being able to teach an old dog some pretty exciting new tricks. So, okay, time to wrap up. I'll just close with a little bit of a warning. Be careful what you ask for. We all want the software we write to be successful. We all want it to be used by many people for many years. but success brings with it costs and constraints that can be really frustrating at times. On the other hand, these constraints, most notably the need to keep the promises you've made to your users, whether you've made them implicitly or explicitly, they force you to spend a lot of time up front thinking about whether something is the right thing to do and what the possible consequences and interactions will be. And most of the time, thinking deeply about something ahead of time pays off. So even if it does mean you can't rush forward as quickly and as you might have otherwise liked to. So thank you everyone for listening. Enjoy the conference and don't break anything on the way out.